Yes. Hello, everyone. The first question: did everyone receive my emails? Mm. Or just one email, actually. Hmm? So I have correct emails of everyone, right? Mm. Mm. Uh, okay. Okay. So let us start. Uh, maybe the first actual question is: does anyone have questions about the last lecture, or everything was clear? So I will actually write some simple problems maybe after each lecture and send to you by emails so that you can solve them and check that you understood everything. Like, for example, for the last lecture, I will give several differential operators and ask to print them to a canonical form. So, like to check how this theorem work in practice. Why any operator of this form can be brought to one of these forms. Right. Actually, I didn't say this, but this can be called a theorem of classification of such differential equations of second order. But as you saw, it is quite trivial in a sense. It's reduced to Gram-Schmidt procedure and some other simple transformations. Mm. But today I would like to tell about possible techniques which can help us to solve equations of such kind. Probably I can erase this. And to demonstrate these techniques, I would like to start from a discretized version of Laplace equation. Namely, we can replace second derivatives of functions with the following expressions. Where this shift operators Ti acting on the functions shift its arguments by one. So and for simplicity, let us say that the number of variables is just 2. Uh, and our function lives on a cylinder. In a sense, we have this integer lattice of size nx by ny. So it's closed in this direction and also in this direction. So we have function which depends on two variables, x1 and x2, and which are integer. And it's also periodic because we are on a cylinder. There is this periodicity condition. And it's clear that such functions are elements of some vector space. And what is the dimension of this vector space? Oh, so this vector space is functions on z over z n1 times z over z n2. So it's isomorphic to c to some power. And what is this power? What are the dimensional spaces of a vector space of functions defined on this finite set of points? Hmm? Because when we think about such differential operators, we think about them in some local chart, local coordinate chart. But if we want to study some actual problems, we need to say what is the domain where this operator is defined, what are the boundary conditions, for example. And so if we think about differential equations, about partial differential equations, for example, we have equation du over dx squared, dx1 squared plus du over dx2 squared time equals to some f. There are many options to define the domain where this equation is defined. For example, we can say that this x1 and this is defined, for example, on a rectangle. X1 goes from 0 to 1, x2 goes from 0 to L2. So this function is defined on such a rectangle. But as we will see in this simple example, in such a case, we need to say something else. For example, we need to say that let's call this rectangle D, and for example, we should say that u on the boundary of this rectangle equals to 0. This is one option. But if we don't want to think about boundary and about boundary conditions for this equation, we can do something simpler. Namely, we can say that this rectangle is actually a torus. Oh no, that we can say that we want to solve this equation on a torus. Namely, we identify this sides of rectangle, and in this case, we don't need to care about boundaries.
What we are doing is specific example posing ourselves in this condition. So we assume that not in the boundary, but by identifying the boundaries of the interval where it is defined, we suppose that the values are the same.
Yes.
And so we study how this PDE can be solved assuming this condition.
Yes. In this case, it's not a PD, but some discrete approximation of it. Yes. And if we choose big enough number of these points and smooth enough functions, then probably we can prove that a solution of this discretized PD will approximate a solution of the actual PDE. And this is what people do with such equations when they want to solve them numerically. So back to this question. What's the dimension of the space of functions defined on these points? And what is so is it clear why these functions form vector space? Like, so our functions, let us call it u. Sorry. So our function u acts from and a structure of the vector space is obvious. If you want to take some linear combination of functions, like lambda1 u1 plus lambda2 u2, and evaluate it at a point x1 x2, it will equal just to pointwise sum lambda1 u of x1 x2 plus lambda2 u1 U2 of x1 and x2. And they also form a structure of algebra because we can multiply them pointwise. But now we need only this vector space structure. And maybe a more general question. If we define a vector space in such a way, like functions on a finite set of points, what will be the dimension of the space and what are the natural basis? Like, we can write another example. Hmm? Yes, thank you. So it is isomorphic to C to n1 times n2. Because it's just a number of of uh, points in this set, and the natural basis which will be useful for us are delta functions. So delta, which is labeled by some points, let us call it x1 0, x2 0. So what is this delta function? This is such a function that when we evaluate it in some point, it is 0, sorry, of x1, x2. It is 0 when x1 is different from x1 0, x2 different from x2 0, or and 1 if x1 equals to x1 0 and x2 equals to x2 0. So we can say that there is such a natural basis where labeled by points of this lattice such that the plot of this function is 0 everywhere and one peak at some point. And the value of this function in this peak is 1. And it's clear that they are linearly independent and that they form a basis in the space of functions on this finite set. So is it fine? So and there is our a difference operator in this case. which is a sum of the shift operators, T1 plus T1 inverse plus T2 plus T2 inverse minus 4 acting on U. So of course this operator acts on this space of functions because it's shift by integer numbers, and since we live on a torus, all these shifts make sense. So this operator acts on this functions of z over z, and 1 times z over z and 2. So now there is a natural question. How do we solve such kind of equation? Like Laplacian acting on U equals F. And since we live in this finite dimensional case, there is a very natural idea. This is some operator acting on the vector space. Actually, let us call this vector space V for simplicity, because we'll use it so the very natural idea is to say that it's a system of linear equations. There's some right-hand side, and some operator acting on the left-hand side. Let us try to say that naively U just equals to Laplacian inverse acting on F. But before doing this, we should ask what is the kernel of this Laplacian? And also, what is the image? So let us go to the so which is simpler. Maybe the first question is simpler. So we need to find such function on this finite set that Laplacian of this function is 0. And let us look at the structure of this operator. It contains 4 shifts and in 4 directions, and here, here. So all this comes with coefficients 1, 1, 1, 1, and minus 4. So let's say that u of x1, x2 equals to 1/4 u of x1 plus 1, x2 plus u of x1 minus 1, x2 plus u of x1, x2 plus 1 plus u of x1, x2 minus 1. And if we want to solve such an equation, we need just to look at this formula and think what it means. This formula says that a function in any point equals to the average value of this function in the neighboring points. And now let us suppose that our function u has a maximum or minimum inside this torus on this lattice. Maybe it's better if I ask this way. Can this function have a maximum or minimum, or its real part? Can it have a maximum or minimum in a torus in some specific point? Like, but suppose that minimum of, for example, maximum of this function is at some point x1 0 and x2 0. And look at this equation. This equation says that u at this point is greater or equal to u at any shifted points. So it says that u of x1 0, x2 0 is greater or equal or of u then u of x1 0 plus 1 plus minus 1 x2 0 u of x1 0 x2 0 plus minus 1. But if this holds, let us just take sum of all these inequalities, and we will come precisely to this equality, which turns into inequality. If you sum this. But we know that this is equality, and it means that any of these inequalities were actually equalities. So all of them are strict equalities. So we conclude from this assumption that function f has maximum at some point to the statement that this function is constant because it is the same at this point and at 4 neighboring points. So is it fine? This is actually the same argument in a differential case. It is the same argument in complex analysis, which says that there are no homomorphic functions on a complex manifold, on a compact complex manifold, other than constant functions. So here it also works in the discrete case. So other.
We just repeat the last part, which includes that the U is constant, and the U is 1 and 0 is greater than this.
We take 4 such inequalities and take their sum. From one side, we get some inequality of this sort, and on the other side, we know that this inequality is actually a strict equality, which means that any of these inequalities were strict equalities, because like we know that this one is greater or equal than this one, and this one. But if we know that they are actually equal, that it means that each term, each of the terms should equal. So, conclusion is that kernel of this Laplacian is C. It consists of a constant function. And now, since we are in the finite dimensional case, we know that if kernel of a matrix is one-dimensional, it means that its image is dimension minus one-dimensional. And the question is, what is the defining equation of its image? So the next question is, what is the image of delta? Like, for example, what happens if I take a Laplacian of u and compute, I can call it integral, but let us say that it is just sum over x1 and x2, Laplacian of u of x1, x2. What happens if we compute such a sum? Yes, thank you. Because any term will be computed, will be counted 4 times in such kind of terms, where they're written in such kind of terms, and minus 4 times when we take this term. So it's kind of a dual statement to the statement about kernel, in a sense that defining a equation for the image of Laplacian, and that it is orthogonal, or yeah, maybe it's better to say orthogonal to a vector which consists of 1, 1, 1, 1, 1. So it's orthogonal to constant element of the dual space. So if we want to make this question meaningful, we need to say that f lies in the image of delta. So let us say that the image of delta is let us call it v prime, and v prime in the set of functions such that sum of xi, x1, x2 x2 from 1 to n2. This sum equals to 0. Actually, it's sometimes or maybe always easier to count from 0. So now if f is in v prime, we can ask for solution of this equation, and for example, look for solutions also in v prime. So this is our problem. And now our idea to look for inverse of the Laplacian is not so naive, because now we know that it does not have a kernel on v prime, because we have already excluded this vector which was in the kernel, and also the right hand side lies in the image of this linear system. So it will have some solution. This solution will be unique, and so it's kind of the first idea of what we can do with the partial difference equations and partial differential equations is to find inverse of this operator. And maybe let us reformulate it some different way. So of course, we can write that u equals to 1 over delta f, and or maybe delta inverse times f, and this is a solution. And this delta inverse is called, at least in the differential case, it is called gain function. So the idea is, and it is called g. So this is a But let us think in more detail about this problem. So, of course, we can write this Laplacian operator as a matrix in some basis and compute its inverse. We can write a program which does this. But let us first think what it is and which equation we should solve to find this. So uh, so how to say it? So this equation which is written here has this form. So it is some matrix acting on a function f. But let us write it in our notations. This u and f are functions on this finite set restricted by some condition that sum of their components is 0. So written in the components, it says that u of x, x1 and x2 equals to, like, here we need to write a product between a matrix and a function. And this product always includes a summation over the basis vectors. And basis vectors are labeled by points of our finite set. So it has this form. So these are the points of our clause. So is this notation clear? So, but now let us think about this gain function. So let us ask which equation is solved by this. We know that if we multiply a function and its inverse, like act with a delta on g, it will give of x1, x oh, so let us act on the first matrix index and keep the second matrix index fixed, y1, y2. So it should be identity matrix. Or in other words, if we write down this identity matrix as a function on this two sets, it will be a kind of delta function again. Oh, by the way, I do know this notation. I've already introduced the notation of delta functions, so I can use it. Will be delta x delta y1 1 y2 of x1 x2, and here you should actually subtract 1 over n1 n2, so that it lies in the v prime. So is it clear why this function is actually a matrix element of the identity operator? So if we multiply some function with this identity operator, and compute it at the point x1, x2, it will equal to this sum over basis vectors y1, y2. So here we see that the second term gives just a 0, because our function has 0 sum. And the first term, okay, it is 0. And the first term is non-zero precisely at one point. Oh, sorry, I have tried here y1, y2. First term is non-zero only in one point, when these two numbers coincide with these two. And this gives us u of x1 and x2. The moral of this computation is the following. If we want to find a green function, or the inverse of, in this case, of this Laplace operator, we need to solve an equation that our differential operator or difference operator acting on this function equals to the delta function, to some function which is 0 in one particular point, and which is 1 in one particular point, and more or less 0 in all other points. So in this case, we had to subtract this simple thing because we ask for functions which have zero sum. And, it was actually our choice because we could find we could look for other functions in uh, we could look for other functions because in principle we can add constant. It will still be a solution of this equation. So we can also think about this way. So if you want to solve this equation for arbitrary function on the right hand side, we can represent this function as a sum of this elementary basis elements. As a combination of delta functions in each point. And if we can compute the effect for the left-hand side from one basis element from one delta function, then we can just take linear combination of all of all such solutions and get this formula. So so this formula says that the function f was first decomposed into a combination of delta functions, and then we solved this equation for each delta function, and then using the fact that the equation is linear, just took some of the solutions and got a solution for arbitrary function on the right hand side. So and this is the same idea also for differential equations. So you see what will be our problem if we try to generalize it to the differential equations. That here delta function is something very well defined. It's just some element of finite dimensional vector space. But if we switch to differential equations, we will need to define what it is, what is delta function. And let us maybe make 10 minutes break, and after this I will tell how to find this grand function for this particular equation, which will also be generalized to the differential case. Are there any questions?
I kind of understand where that 1 over 9, 1, and 2, 9, 1, and 2 comes from.
Because here we had so where was it? This equation had a kernel, a constant function, and to make a solution of this Laplace equation uniquely defined, we asked this to have zero zero sum of components. So actually, well, actually, so let me think. No, sorry, it's a different fact. our Laplacian gives functions with zero sum of components. So if you try to find a solution of equation with just a delta function in the right hand side, we will fail because the sum of its components is non-zero, and it does not lie in this space V prime. So we should solve this equation with the kind of corrected delta function, and it is corrected by this term. And we can check that if we act on this operator on the space of functions in V prime, we again get a function in V prime. So. So how to say it more accurately? So if to say it more accurately, it looks like this. We have V which lies in V prime, or V prime which lies in V, and we can say that V is a direct sum of this constant function. Let us call it 1, 1, 1, 1, 1, or constant, plus V prime. And this constant is in the kernel of delta. So so when we solve an equation delta times g equals 1, this actually means that this 1 in the right hand side is a function from V prime to V prime.
So when you sum all of them, you obtain zero.
Yes, so it is 0 on this component. Like this. So, are there any other questions? No, actually, do you need a break, or shall we continue? Or what do you think? Hmm? Mm-hmm. Yeah. Yeah. So, So, by the way, I don't remember. Do I have your email or not? Probably no. So, you know, and everyone else. Yeah.
We didn't talk about it, but do you have any information or the exam how it be like oral or written?
Yeah. Mm, mm. Well, far as I remember, originally it was some kind of mixed exam, like you should write something and then explain what is written. But actually need to check. I'll probably ask. So I'll tell you next time. Okay, so uh, here was the first idea that to solve such equations, like Laplacian acting on some function equals to something, we need to compute the inverse matrix, which can be represented as a solution of this equation. But now the question is how to compute inverse matrices. So and how in general to compute some functions of matrices. So, as you might remember from the linear algebra, if you want to do something like this, it is usually quite convenient to, first to diagonalize the operator and then look for its inverse or for some functions of the operator. So let us try to do the same in our situation. So how to diagonalize delta? Yeah. So we see that it is a sum of five operators. One is already diagonal. It is um, a constant matrix, but there are also T1 and T2. So mm, and we can do this. We can diagonalize them at the same time because they commute. So is it clear why they commute? Hmm. Like it should be clear from the definition, because 1 plus T1 times T2 on F equals to F of x1, x2, x2 equals to F of x1 plus 1, x2 plus 1, and in the same in the opposite order. So it should be kind of obvious because T1 and T2 are translations in these two directions, and T2 to 1 in these two. So this idea too, which is used everywhere, is the following. Uh, how to say it? Do separation of variables. So what we will see here, it will be a Fourier transform. So, and the idea is precisely this one. In this particular case, this idea says that we need to find several operators which commute with each other, and diagonalize all of them. So in the simple case, our Laplacian was just sum of these two operators, and we will see later there can be more complicated situations when we first diagonalize one operator and becomes some number, and this number enters in some non-trivial way the other operator. For example, well, we could imagine a term like T1, T2 here. So we first diagonalize T2, and after this we diagonalize operator involving T1 and T2. No, maybe it's too trivial example, but we will just see how it works in the differential case, because I don't know corresponding different examples. So what is precisely meant by this idea that we should diagonalize the separators? We need to find such a function which is eigenfunction for both of the separators. Namely, we say that there is some phi which will denote phi k of x1 and x2, such that t1 times phi k of x1 x2 equals to lambda 1 phi of x1 and x2, and t2 times phi k of lambda 1 of k of x1 x2 equals to lambda 2 of k phi of x1 and x2. And Practically, this means that we need to find such function of k that phi of phi k of x1 plus 1 x2 equals to lambda 1 of k phi of x1 x2 and phi k of x1 x2 plus 1 equals to lambda 2 of k phi of x1 x2. So the first question, if we know that these functions lie in V prime, phi k, k, k lies in V prime, in the space of functions defined on this discrete torus with zero sum of components. What can we say about these eigenvalues? Is there any requirement coming from the periodicity condition? Like here we had these periodicity conditions written here. So can we say something about this two eigenvalues, lambda 1 and lambda 2? Mm-hmm. Of course. As a square. No, what do you mean square by square? Yes. So what does it say about this eigenvalue? Mm-hmm. And the same for lambda 2. Perfect. So there are two rods of unity. And now let us say which rods of unity they are. So there is some parameter k which I have not specified yet, but let us say that lambda 1, let us parameterize it this way. Lambda 1 is e to the 2 pi I over n k1 over n1 lambda 2 is e to the 2 pi I over n2 k2. And this k1 and k2 are integers, and let us for a moment say that k1 k1 k2 are integers. So now the question, we assume that eigenvalues can be of this form. And the question is, can we present such functions which are eigenfunctions with these eigenvalues? So what is this phi which has the same eigenvalues under these two shifts? Like phi k of x1 and x2, what does it equal to? Mm-hmm.
Started from case 1 is 2, and then by applying 1 and 2, we have lambda 1, and then we construct of this.
So what do you propose? Let us say that there is some value of this function at some point, for example, 0, 0, right? And we need to find its value in all other points. So let us say that if phi k of 0, 0 is 1. Uh, Actually, it's not the best choice. So and then iterate on these equations, we can find that phi k of x1 is it visible when I write here or not? So if I write phi k of x1 x2, it should equal to lambda 1 to x1, lambda 2 to x2, right? And so let me erase something, maybe this part. So continuing this equality, we can write that phi k of x1 and x2 equals to e to the 2 pi I x1 k1 over n1 plus x2 k2 over n2. And we see from this equality that since x1 and x2 are integer numbers, so this function is actually periodic in x1, it's n1 periodic, but also from the same reasoning, it's periodic in k2, in k1 and in k2. So it means that k1 and k2 lie in this in the same set, and one z z over n2 z. Oh, by the way, are you familiar with this notation? So it's in this case it's a Abelian group for n, but it's also a ring, but we don't need this ring structure. So just integer numbers modulo n1 and modulo n2. So precisely this set drawn here. Okay. So we have this basis functions, and of course they form a basis because they have different eigenvalues for different operators, and the number of such functions is the same as the number of these delta functions because they are labeled by the same numbers. And if you want to describe this space V prime, we can see that there is one function phi 0 of x1 and x2. Maybe let me write it in this pair as a vector. This is which is just 1. So v prime is the span of phi k's of x with k different from 0. So this is this natural basis in the space of functions, and we can check that since both shift operators are diagonalized here, then Laplace operator acting on this function actually. I did not think about this before, but this notation is quite ugly. I don't want to keep this n1 in the denominator everywhere. So, sorry for changing the notation. Let me write it this way. Let me say that n1 k1 is integer and n2 k2 is integer. Because otherwise it's very annoying. So let us remember that this momenta, these numbers are called momenta, are now from 0 to 1, and they are non-integer. So, sorry. Okay, so if we have this basis, it's natural to introduce coefficients of expansion of a function in this basis. Namely, we can say that some function of x1 and x2, x1 and x2 equals to the sum over k1 and k2 e to the 2 pi 2 pi I x1 k1 plus x2 k2 actually so let me think. Well, let us go this way. So this f is called f tilde, and this is a Fourier transform of f. So this formula is a definition of f tilde. So it's expansion of our function over some other basis. And let us try to find the inverse expansion. Like, no, maybe we can call it a theorem, but all the theorems are actually trivial. That the inverse transformation is given by almost the same formula. So f tilde of k1 and k2 equals to 1 over n1. Actually, okay, it's not very nice that we will have this 1 over n1 and 2 here, but I don't care actually. Or maybe so. Oh, well, let us better change this notation a little bit here. Sorry for doing this again. I would like to add 1 over n1 and 2, this normalization factor, in this formula. Yes, so let us do it in this way. And here. So the inverse transformation is given by the same formula, but without n1 and 2 in the denominator. x1, x2, and with opposite sign in the exponential. Minus 2 pi I, x1, k1, x1, k1 plus x2, k2, f of x1, x2. So let us prove this statement. Probably I can erase something. Maybe no, erasing kind function is not a good idea. We maybe erase this. So what we need to think? We need what we need to check. We need to substitute this f tilde to this formula and check that as a result we will get the same function. So let us do this. So we have we have this f tilde, and we want to ask what it equals to. We need to check that it is actually f of x1, x2. So let us take this first formula. This is sum over k1, k2, 1 over n1 and 2 e to the 2 pi I x1 k1 plus x2 k2. Then we substitute f tilde, and here we should choose some different summation index because x1 and x2 are already used. So this should be e to the y1 y2, e to the minus 2 pi I y1 k1 plus y2 k2. F of y1 y2. So we now have a double sum, or in k's and in y's. So it is a sum of y1 y2 f of y1 y2 times sum over k1 k2 e to the 1 over n1 and 2 2 pi I k 1 x1 minus y x1 minus y1 plus k2 x2 minus y2. So there's a product of two sums, and let us compute. Let us take this part of blackboard and compute one of these sums. So we need to compute sum over k1 e to the 2 pi I k1 sum delta x1, like some delta x. We can call this maybe z1, k1 z1. And this sum goes over in case 1 over n1. The sum goes over case which are integer numbers over n1. So let us write it back as sum over n1 from 0 to n1 minus 1. Sorry, n1 1 over n1 e to the 2 pi I n1 z1 over n1. So this is a geometric progression, and it can be easily computed. It is 1 over e to the 2 pi I z1 over n1 1 minus e to the 2 pi I z1, and here divided by n1. But actually it makes sense to do only when z1 is non-zero. Maybe it's better to write it this way. Mm. So, so the first question, what does this equal to when z1 is integer and z1 over n1 is a non-integer in this case? Hmm? Yes, thank you. Because this one is 0 and this is non-zero. But and when z1 over n1 is integer, it means that all these terms are from the very beginning ones. We just take a sum of n ones. Mm. So, and in this case, it is 1. So, but since this points by on a torus, we're saying that z1 over n1 is integer is the same as to say that it is 0 after this shift. So we can say that the sum, so the answer can be formulated this way. So the answer for the sum can be shortly formulated that this is delta or kind of delta 0 of z1 maybe, or it's a stupid notation, but probably it's clear. So it's a function which is 1 when z1 is 0 and 0 otherwise. This can also be written with the delta chronometer symbol, like delta z1 0. It's the same. So, as a result of this computation, we get that sum over, we get here sum over y1, y2, f of y1, y2, delta of x1, y1, delta of x2, y2. So taking the sums, we get only one term when y1 equals to x1 and y2 equals to x2. So the answer is that if it is f of x1 and x2. So this is actually the inverse transformation of our function. And so, are there any questions? Hmm? Mm, this? Oh.
Yes, we have 1 over n1 as a coefficient.
Where?
Everything is divided by n1.
Here? Oh, where? We take sum of n1 identical terms. This is precisely why it is here. Yeah. Actually, another choice of this normalization is to put a square root of n1 and 2 both in the inverse and direct Fourier transform. It's so there are all the different notations. There's some other notations for continuous Fourier transform, and maybe I'll say a few words about this later. Uh, for example, when we make it symmetric, then it turns out that we can consider this Fourier transform as just some abstract operator acting on the space of functions. And since inverse and direct Fourier transforms look almost similar, it makes sense, for example, to apply a direct Fourier transform twice and see that it is an operation which changes the sign of function. And if you apply it 4 times, it maps a function to itself. So if you ask about this, if you treat it as some abstract matrix, we can ask what are the eigenvalues of this matrix, and we realize that since its fourth power is 1, then this eigenvalues should be i's, minus i's, ones and minus ones, and we can ask, for example, what are the eigenfunctions of this operator. But this is some funny problem which can also be formulated for functions, but I don't know if it has any practical application. So just funny to know that it exists. But anyway, maybe the last point for today. So why this Fourier transformation is nice. So our primary problem was to solve the equation Laplacian of u equals to f. Now let us try to realize this equation using this Fourier transformation. Namely, let us say that u is expressed in terms of its Fourier components. U of x1, x2 is sum of k1, k2, 1 over n1 and 2 e to the 2 pi I x1 actually the sum is also denoted by a scalar product of these two vectors, k times x or x times k. So it is e to the 2 pi I k times x u tilde of k. And actually also here we can use this vector notation. And also here. And now let us act with the Laplace operator. So we see that these exponentials are precisely eigenfunctions of translation operators which are present in our Laplacian. So if we act in x, and this is x here, and we act with the Laplacian in x. So Laplacian acting on u of x is sum over k 1 over n1 and 2. So here write the eigenvalues of this shift operators. E to the 2 pi I k1 plus e to the minus 2 pi I k1 plus e to the 2 pi I k2 plus e to minus 2 pi I k2. And here same function, u tilde of k. So we see that. Oh, sorry, I forgot to subtract 4. So we see that if we now perform the same transformation with the right-hand side of equation, if we substitute f as the same series and write that left-hand side equals to the right-hand side, we get a very simple formula. So probably I'll erase all this. Uh, The consequence of this is that u of u tilde of k equals to f tilde of k over, let me combine these exponentials into a single function, to cosine of 2t k1 plus 2 cosine of 2t k2 minus 4. So I kind of solved this equation. And I remember we had initially this problem that our Laplace operator had kernel, and this equation could not have solutions for some functions. And we can actually see this problem in this formulation as well. When k equals to 0, this denominator is 0. So it means that f tilde of 0 should be 0. But if you look at the formula for f tilde here, we see that f tilde of 0 is precisely the sum of values of f in all points. So maybe that's all for today. So the one thing which remains at the moment is to combine these two approaches. So here we learned how to solve this equation using a Fourier transform. That we should take Fourier transform on the right hand side and divide it by this function, and then take inverse Fourier transform. But we can also apply this approach to this delta function. And actually, the answer is that we should just put 1 here, and it will be the answer. Are there any questions? Okay, so for the attention. Okay, hello, goodbye.